Hi, I assume that all you want from your organization is to be profitable with good margins, to create actual value, and to deliver revolutionary products and services that make an actual impact on the society. But in reality, you are struggling with high cost, quality issues, long lead time, internal conflicts, and talents that just run away. So if this is the case, please keep on watching this video because I may have something for you. Just a little note before we start, I will put the focus on embedded software development area because I have expertise mainly in there, but I promise you that control theory is ubiquitous and it applies in a lot of other fields ranging from system biology to economical system and including many more other fields. So let's start by looking at where we are nowadays as a society. If we watch the TV, or for those who still have a TV at home, of course, or if we surf the web, or if we just walk around, we notice that we are flooded by a huge amount of technology that is supposed to improve our life quality. But is it always the case? I mean, how often we get mad, for example, with our smartphone that does crazy things without being asked, or with failing products, or with services that get stuck and that are actually not really improving our life. I am fairly confident that we all experience that, right? So what does it mean? Well, it means that the reality, essentially what we deliver, doesn't really meet the customer expectation, and so at the end the customer are not so happy, right? But what about the development side? Namely, are the workers that every day collaborate for creating these technological things any happier? Well, to figure it out, let's take a look on how a typical high-tech product is developed nowadays. So perhaps the most popular scheme for developing systems is the V model, and I will take that as an example. Now, if you Google, you find different representation of this model, but it pretty much goes like this. Imagine that we want to develop a super cool product that includes a lot of cool features. Like for example, imagine that we want to develop a smartphone that is capable to run a lot of apps in parallel while reading the most interesting news for us and things like that. Then these requirements are broken down into more refined and smaller requirements, and at some point we start with the actual product realization. Now, as long as we proceed with the product realization, we need to test the current solution against the requirements, and this happens at each level in the right hand side of the V model. And this happens in theory. In practice, things are a little bit different. Take a look. So what we have at the end, this is from a customer side, and yeah, you get it. So at this point, someone can say, yeah, okay, sure, but you know, you used the V model. If you go agile, all these things don't happen. Well, no. I mean, by going agile, you rule out all the requirement administration thing, but the iterations, software updates, test, fail, patch, test again, and bug fix and test is still there, and you may still have a software that grows uncontrolled. However, I'm a big fan of Agile, and in a future video I plan to express what is, in my opinion, the real benefit of using Agile. To make a small recap, we can conclude that we have unhappy customer on one hand and stressed workers on the other hand. it is clear that we have to make a change. But to make a change, we need to figure out first why all this mess happens. And the answer is easy. It's about complexity. It is undeniable that today's apps are way more complex than in the past. Like, for example, if you consider the electrical system of an old car, it was made by some lamps, a few switches, some meter of cables. While nowadays vehicles, they have a lot of sensors, actuators, they have computers on board, they communicate to each other, they are connected to the cloud and other crazy things. The problem of such increasing complexity is that it brings huge challenges that our employees cannot overcome. Then they get stressed and then they eventually burn out. And we know that burnout is a sad reality nowadays. Easy as that. So we need to think something new. Or maybe not. Are we sure that people never had the big challenges in the past? I mean, for example, if I say, what about making an airplane to fly, or allow two guys located mile away to have a real-time conversation, or even sending a man to the moon and let him back alive, if you consider the historical context and available resources at that time. But yet they made it, right? And they also left some interesting message. I would not be surprised if you don't remember those messages. Because come on, let's be honest, who is going to read the lesson learned? We never do that. When we have a problem, we go straight in finding a solution ourselves without looking if someone else already encountered that problem. This is the way we roll. Let's be honest. But still, history is written and we can look into that at any point in time. So this time I suggest let's be humble a little bit and let's take a look to the past. We all know that the early years of last century saw a rapid and widespread of new engineering applications. However, the engineering focus at the time was mainly devoted to hardware development, namely to component sizing, component development, material choice, packages, and things like that. And the part on how to orchestrate everything was a little bit under the radar. But still, they need some device to make the whole system to stand up. And the task of these devices were essentially to automatically manipulate some quantities, like for example voltage and current for keeping a certain speed in electric machine, or to change some mass flow for controlling some temperature and pressures in heat exchanger, or to move some actuators for self-stabilizing ships and things like that. As said, this was an underestimated problem, and for engineers at that time, it was enough to use some switch, relays and valves that changed their status according to some sensor measurement and according to some intuitive and heuristic rule. An example of such a rule could be like if the temperature at point A in a boiler is too high and the pressure at point B is too low, then turn off switch X and slightly open valve Y. So this is the way governors were intended. But then, as application multiplied, engineers became more confused because things were not working any longer. I mean, controllers that were working very well under a certain condition were not working under different conditions, or even when there were a change in some small part of the system. So, to cope with this problem, they use a brute force method. So they start to add more logic, more switches, more valves, and ending up in solutions that were complex, expensive, difficult to maintain, and simply that nobody could understand that. Some smart guy at that time observed that when the system were operated manually, the operator were not using an on-off approach, but rather you observe the system and gradually reduce the actuation power when the system was approaching to a desired set point in a very smooth way. And then someone started to understand that in the design of complex system there were some hidden challenges that needed to be addressed properly. Then, between 1935 and 1940, advances in understanding control system were mainly independently in different parts of the world, but the most influential work came from three groups in US. So the first one was made by electrical engineers at Bell's Lab. At that time, AT&T was finding a way to extend the bandwidth of their communication system. In the 1940, a guy called Hendrik Bode was studying design methods in the frequency domain and came up with the so-called Bode diagrams, and he introduced important concepts like gain and phase margin that are extremely important nowadays in control. The second group were mechanical engineers and physicists working in the process industry. Encouraged by Ed Smith at the Builders Iron Foundry Company, they began to develop a systematic understanding of control design methods, and they also attempt to establish a common vocabulary. The third group was at the electrical engineering department of MIT, and this group was led by Harold Hudson and Gordon Brown. So they started to develop time domain methods and to use block diagrams. And nowadays everybody uses block diagrams, but at that time it was not obvious to use block diagrams. And in addition to that, they start to simulate systems by means of a differential analyzer. Then we all know that the Second World War arrived, and all the control effort suddenly shrink into few applications, where the most important was the anti-aircraft guns. So that was a complex problem because it included the detection of the position of an airplane, compute the future position, and also to make a precise movement of a heavy gun, right? And for that, all the development that were around convey all together, and the activity was multidisciplinary because it included electrical engineers, mechanical engineers, physicists, and so on. And at the end, they made it. The lesson learned after the Second World War, it was conclusive. I mean, you cannot control complex systems just by following intuition along a trial and error approach, but you need a systematic methodology, and it has been proved the superiority of control theory methods over any other method. The details of the work carried out during the Second World War was published in a seminal book which is called The Theory of Servo Mechanism, and in 1957 the International Federation of Automatic Control has been established. At that point, control theory was taught only to a very narrow audience made by graduate students, and only later on it became a standard subject in engineering courses. The Second World War experience fueled the curiosity of a number of people, and new questions arose. And many of these questions were also a little bit philosophical, if you want. For example, the problem on how to design a stabilizing controller became how to design the best controller, right? But philosophically speaking, what does it mean, the best controller, right? So along this line, a lot of other questions pop up and arise, and a new area in control has been established, like for example optimal control, robust control, and so on, as well as important concepts like reachability and observability. And I can tell you that nowadays there is still interesting research in control, and there are still open questions that need an answer. Okay, now hold on. I hear you. Someone is thinking, nice history, but time has changed. We are not living in the 1940s any longer. Well, you're right, but this does not mean that good old classic control theory is not used today. In fact, those who didn't forget the lesson today are doing some interesting things. Take a look. But come on, Ubaldo, don't cheat. This must be some artificial intelligence thing or machine learning or something which is much more modern. Cannot be classic control theory.
No deep RL so far. In fact, they're not using any machine learning technology on that robot. Incredibly. You heard the man. So what are they using? They're likely using a stack of very carefully hand-designed classic control laws. Classical control theory provides us with strong mathematical guarantees.
So I imagine that now you're asking the question, but why, if control theory is so powerful, is not widespread in industry? I mean, at the end, we have some employees that they took some control theory class. Well, this is true. But the thing is that I think that one of the main reasons is that it's because of how control theory was taught in the university in the past. Because control theory is a bit abstract and theoretical at first glance, it's not immediately straightforward to connect to the reality. And unfortunately, people that were teaching control theory in the past were mainly researchers or top students, that they were eventually very good in control theory, but they don't have a good pedagogical approach for teaching the subject. Nevertheless, engineering institutions like IFAC and IEEE recognize the importance of providing a good control theory education and are actually working on that. And to be honest, I'm also contributing as well from what concerns industrial settings. Next, let's talk about the deployment of control theory into your organization. So, first of all, you have to understand that control theory is not just a collection of methods and tools for solving problems, but it's more a mindset. It's a culture, let's say. And deploying control theory in an organization represents a huge challenge in change management, because it is going to reprogram the way employees think when they are facing their problem, and that's not easy, of course. On top of that, control theory results are often counterintuitive, and the risk of putting people into conflicts or making them not believing you as a leader because of your crazy idea may be large. So be ready for this if you plan to go that route. Another obstacle is represented by the fact that control theory is strongly based on mathematics, and notoriously we know that people tend to not like mathematics. But in reality there is also a deeper aspect here, is that mathematics leave little room for debating. It gives real and crystal answers, like it or not, right? And unfortunately, we have to acknowledge that in every workplace there are people that they don't really like when things start to become too much transparent. You understand what I mean? Finally, during your process of deploying control theory in your organization, you may start to have some problem with some resource that you cannot, because you cannot raise their competence to the right level. Then in that case, there will be a lot of suppliers that may come and they promise you some magic tool that with just a right click you get your controller for free and all the problems are solved. Well, things don't work like that. Control theory is a craftsman work and the solutions are tailored on the problem. So the only way is to learn this craftsmanship art. Sorry for that. Anyway, now imagine that you deploy control theory in your organization. Bear in mind that there are still some risks. So the first one, at least in my experience, workers who learn a new topic in control, then they want to use that method for solving all the problems. And this may end up in having people entering into conflicts because there are these hardcore control guys that they want to use as a sledgehammer to crack a nut. This can happen, actually. In reality, an experienced control guy, he knows what is the best solution for the given problem, and he always tries to find the simpler solution. So, if something works with a switch, go for it. The problem is that, are you sure that it's going to work with a switch? If so, how you justify this incredible growth in embedded software, for example, or in other area? It's the same. Why your organization needs control theory, which is the title of this video. Well, we need it for avoiding a situation like this. Now it comes that if you manage to avoid this type of situation, then you can reduce the cost, you can reduce the quality issue, you can create a better work environment because you reduce also the misunderstandings, plus a lot of other benefits. So control theory can really help your organization to make a big step ahead. But control theory is not only for engineers. In fact, it may help you to see things differently, to think out of the box and to take better decisions. Because in fact, control theory is all about decision making. Now, with this channel, I don't want to take the mathematical route as it is typically done for explaining control, but I want to take a philosophical route so that everyone can understand it and hopefully can use it in their life. So, in my next video, I don't know when I will make it, to be honest, but I will continue the journey in control theory by explaining what is control theory. So, if you like this video and you want to be updated on when a new video is released, please subscribe to the channel and hit the bell icon. And what else to say? Thank you for watching.